Hello, we are Group 8 and this is our final project presentation by Hayal Roman, Charmaine Joy Rains, Sylvia Wang, and Kwok Kan Ho. And my name is Hayal Roman and I will be starting with the background. The paper, The Case for Ramp Clouds by John Osterhout is grounded in the growing limitations of traditional disk-based storage systems in large-scale applications. Although data volumes have rapidly increased, disk access speeds and latency improvements have lagged behind, creating significant performance bottlenecks. To cope with these limitations, developers rely on complex techniques such as caching and sharding, which adds system complexity without consistently solving latency issues. This mismatch between modern application demands and storage capabilities motivates the need for a new approach. As a result, the paper explores a shift toward in-memory distributed storage to achieve both high performance and scalability.
In large-scale web applications, performance is very important. These systems need low latency, which means fast response times, and high throughput, meaning they can handle a lot of requests at once. However, traditional disk-based storage systems create a major bottleneck. Disks are much slower compared to memory, so accessing data takes longer, which introduces delays and slows down overall system performance. To deal with this, many current systems use layered architectures, like combining databases and caching systems. While this helps to improve performance somewhat, it also makes the system more complex and harder to manage. Even with caching, performance is not always consistent, especially when there are cache misses. Because of these limitations, the authors propose redesigning the storage architecture entirely. Their solution is to use distributed in-memory storage called RAM Cloud, which keeps data in memory instead of relying on disks. This approach aims to make systems faster, simpler, and more scalable, especially for modern applications that require quick and efficient data access.
Hi, my name is Kwok Kang Ho, and I'm going to talk about the core ideas of RAM class and how it actually works. The main proposals on this paper, the case of RAM class is very bold. Instead of storing data in slow disks like traditional systems, the authors want to keep all data entirely in DRAM. That is the main memory of the servers. RAM class is a distributed storage system that combines the memory from thousands of servers into one large unified system. From the outside, applications see it as a single fast storage service, even though the data spread across many machines. The key points on this slide: all data lies in DRAM for extremely low latency in range of microseconds. Disks are used only for backup, not for normal read-write operation. This design removes the need of complicated coding layer and sharding that the developers currently struggle with. In short, the authors are proposing a complex shift move from disk-based storage to fully memory-based distributed architecture that's much faster, simpler, and easier to scale. Next, let's look at how RAM Cloud actually works. The system stores all active data in DRAM across many distributed storage servers. This completely eliminates the slow disk access that bottlenecks traditional systems. Data is automatically partitioned and distributed across the servers, but the whole thing appears as on one single unified storage system to the applications. When an application wants to read or write data, it sends a request using low latency RPC remote procedure code over the network. For reliability and durability, RAM Cloud doesn't keep multiple full copies in memory all the time. Instead, it uses replications of lost data to backup copies on all the servers eventually to disk. If a server crashes, the system can recover very quickly by pulling the backup data from across the cluster.
Hello, my name is Charmaine Rains, and I will be discussing what the authors are proposing. The authors of the case for RAM clouds propose a new approach to data storage in large-scale systems called RAM cloud. In this model, all data is stored entirely in main memory, or DRAM, across many distributed servers instead of relying primarily on traditional disk-based storage. The main idea behind this is that disk-based systems are becoming a bottleneck for modern applications. As web applications grow and require faster response times, traditional storage systems struggle to keep up because disks have slow access times and limited throughput. By shifting storage into memory, RAM Cloud aims to fundamentally change how data is accessed and managed. Instead of constantly waiting for disk operations, the system can access data almost instantly, which makes it much more suitable for large-scale and high-performance applications. So you may ask how it works and why that matters. By keeping data in DRAM at all times and using disks only for backup, RAM Cloud is designed to achieve dramatically lower latency and much higher throughput. The authors mentioned that this approach could be anywhere from 100 to 1,000 times faster than traditional disk-based systems. Even though everything is stored in memory, the system still maintains durability and availability by using replication and backup techniques. This means that data is not lost, even if a server fails, which is an important concern when relying on memory. Overall, the authors are advocating for a major shift in how data centers handle storage. They argue that this memory-based model can simplify application development, support more powerful data-intensive applications, and better meet the demands of modern cloud computing systems. This idea connects to what we've learned about disk limitations, because instead of trying to optimize slow disk operations, RAM Cloud avoids the problem by removing disks from the critical path altogether.
The authors do not test their idea directly. Instead, they support it through a system design, reasoning, and comparisons to existing technologies. They propose how a RAM cloud system would work at scale rather than building and evaluating a real system. They discuss performance metrics like latency, throughput, and recovery time, but these are projected outcomes, not measured results. The authors argue that storing data in DRAM could achieve microsecond level latency and much higher throughput than disk-based systems. They also suggest the system could scale across thousands of servers and handle large data sets. For reliability, they propose replication and backup techniques for fast recovery. Overall, the authors argue that RAM-based storage system could be both practical and significantly faster than traditional disk-based approaches.
Hi, this is Sylvia, and I'm going to talk about some research issues that should be addressed before a practical implementation of RAM Cloud can be achieved. One issue is lowering the latency of remote procedure calls, the communication method of RAM Cloud. Currently, the network infrastructure of most modern data centers, typically Ethernet, IP, or TCP based, is too slow. On average, a call would take 300 to 500 microseconds, but RAM Cloud requires latencies of 5 to 10 microseconds. To solve this, the author suggests modifying the TCP protocol, using a different protocol, or making a custom protocol optimized for RAM Cloud needs. There are also other bottlenecks to low latency. For example, The high software overhead from interrupts, context switching, and network protocol stacks can be reduced by having specialized hardware. Also, if virtualization is used, latency could be reduced by having incoming packets bypass the guest operating system and virtual machine, which act as middlemen to the application. Another issue that must be considered is how to make RAM Cloud both durable and available. For example, a single crash should not crash the whole cloud, and a power failure should not cause much data loss. To store backups, the authors considered two ways. One is replication, where copies of each object are stored in the DRAM of other servers and updated with every write request. However, this method will take a lot of memory and energy while also not being foolproof, since at least one backup must dodge a power failure if it happens. The other way backups could be stored is buffered logging, where backup copies are stored on disks of other servers and logs are initially written to DRAM, then saved in batches to disk later. In case of a power failure, objects can be reconstructed using their old version and log entries on disk. The authors also discuss ways to handle power failure, such as flushing data to disk if advance warning is given, tolerating data loss if buffered logging is used, or saving data to disk on each write. There's also the question of what data model RAM Cloud should use. Current existing models suggest an inherent trade-off between scalability and usability. Simpler models such as key value stores are more scalable, but may be harder for applications to use if complexity is required. For RAM clouds, the authors suggest an intermediate approach where servers don't understand object structure but do support object aggregation and indexing. Another issue that should be considered is distribution and scaling. RAM Cloud must appear as a single system despite being thousands of servers. As a result, data movement between servers must be automatic without impacting application performance. The authors note that this process could be simplified if buffered logging is used, since data could be copied to another server at leisure and updated based on logs. In addition, the authors write about how to maintain consistency on a large scale. Currently, there is a trade-off between scalability and consistency. Highly consistent methods such as ACID, which is used by relational databases, are reliable but don't scale well. As a result, alternate approaches such as Bittable and Dynamo sacrifice a little consistency to improve scalability. The author suggests that RAM Cloud has an advantage in this trade-off since its low latency may make consistency cheaper. For example, it could scale to a larger degree before ACID becomes too expensive to implement.
Open questions we had as a group were: do the author's predictions reflect the complexity and variability of large-scale production systems? It's possible, but saying RAM Cloud will be a major game changer for AI infrastructure in the near future might be a bit optimistic. What are potential risks or trade-offs of relying entirely on in-memory storage like RAM Cloud?
In conclusion, the paper outlines a case for RAM Cloud. Over time, data volumes have grown rapidly, but disk latency and access speeds have not kept pace. Keeping storage entirely in DRAM would avoid the limits of traditional disk-based systems and comes with benefits such as low latency. This paper also discusses challenging issues that need to be addressed when making a practical implementation and offer their own suggestions to each question. They discuss issues such as how to achieve low latency, how to maintain durability and availability, and what data models to use, among other issues.
That concludes our presentation on RAM Cloud. Thank you so much for your time and attention. We hope this gave you a clear understanding of the limitations of traditional disk-based systems and how RAM Cloud offers a faster and more scalable solution. This presentation was brought to you by Group 8, Hayal Roman, Charmaine Rains, Sylvia Wang, and Kwok Kan Ho. We appreciate your time and we're happy to answer any questions. Thank you.